the video regarding the tricks for hybridization and lone pair of organic and inorganic molecules. To calculate the hybridization of any given molecule, first we will calculate the total number of valence electrons of all the atoms of the given molecule. When we will calculate the total valence electron, then we will check if the total valence electron is less than 8 and greater than or equal to 2. If the total number of valence electron resides between 2 and 8, then divide the total number of valence electron by 2. If total number of valence electron is between 8 and 56, then divide the total number of valence electron by 8. And if the total number of valence electron is greater than or equal to 56, then divide the total number of valence electron by 18. When we divide by 2, 8 and 18, the number which we get will be the number of hybridized orbitals. To calculate the lone pair, we will subtract the number of surrounding atoms from the number of hybridized orbitals. The concept will be more clear on seeing few examples. Our first example is methane, CH4. The valence electron in carbon is 4 and the valence electron in each hydrogen is 1. As there are 4 hydrogen in CH4, so the total number of valence electron in methane will be 4 plus 4 into 1, that is 8. Now as the 8 comes in case 1, so we will divide 8 by 2, so we get 4. Now 4 is the number of hybridized orbitals. So the hybridization of methane CH4 will be sp3. Now to calculate the lone pair, we will subtract the number of hybridized orbital and the number of surrounding atoms in the molecule. The number of hybridized orbital is 4 and in molecule of CH4, 1 carbon is surrounded by 4 hydrogen. So total number of surrounding atom is 4. Therefore lone pair in CH4 is 4 minus 4, that is 0. Our second example is PCl5. Phosphorus contains 5 valence electrons and each chlorine contains 7 valence electrons. As there are 5 chlorine, so total number of valence electron in all the chlorine in PCl5 will be 35. So the total number of valence electron in the molecule of PCl5 will be 35 plus 5, that is 40. Now 40 is between 56 and 8, so it will be divided by 8 and that goes by 5 times. As the number of hybridized orbital is 5, so the hybridization of PCl5 will be sp3d. Now to calculate the lone pair, number of hybridized orbital, that is 5, minus number of surrounding atom. In PCl5, one phosphorus is surrounded by 5 chlorine. So the total number of surrounding atom in PCl5 is 5. Therefore the lone pair is 5 minus 5, that is 0. Now our third example is NH3 ammonia. Nitrogen has 5 valence electron and each hydrogen has 1 valence electron. As there are 3 hydrogen, so total valence electron in the molecule of NH3 will be 5 plus 3, that is 8. 8 will be divided by 2, that goes by 4. As the number of hybridized orbital is 4, so the hybridization of NH3 is sp3. Now to calculate the lone pair, number of hybridized orbital, that is 4, will be subtracted by the number of surrounding atoms. In NH3, nitrogen is surrounded by 3 hydrogen. So the total number of surrounding atoms in NH3 is 3. So the lone pair will be 4 minus 3, that is 1. Our fourth example is ammonium ion, NH4+. the total number of valence electron will be 5 plus 4 minus 1. 5 is the total number of valence electron in nitrogen, 4 is the total valence electron of 4 hydrogen, and the plus sign means that nitrogen has donated its one pair of electron, so minus 1, that is total 8. 8 will be divided by 2, that goes by 4. As the number of hybridized orbital is 4, so the hybridization of NH4 plus will be sp3. Now to calculate the lone pair, number of hybridized orbital is 4 and the number of surrounding atom is also 4, as in ammonium ion 1 nitrogen is surrounded by 4 hydrogen. So total number of lone pair will be 4 minus 4, that is 0. Our fifth example is XeO3. Now XeO3 has total number of valence electron of 26 and the 26 will be divided by 8, but 26 will not be completely divisible by 8, so we will divide as follows. 26 will be divided by 8, it goes by 3 times, that is 24, and the remainder is 2. Now we will again divide 2 by 2 itself, so the remainder is 0. Now to calculate the total number of hybridized orbital, we will add both the quotient, that is 3 and 1. Now the total number of hybridized orbital will be 3 plus 1 is equal to 4, that is sp3 hybridization, and the lone pair will be 4 minus 3 is equal to 1. 4 will be the number of hybridized orbital in XeO3 and 3 is the number of surrounding atoms in the molecule of XeO3. In XeO3, one xenon is surrounded by 3 oxygen atoms. So the lone pair is 4 minus 3, that is 1. Now the final example is I3 minus. The total number of valence electron in I3 minus is 22. As we can see that I3 minus has a negative charge, so it must have accepted electrons. So in calculation of total valence electron, we will add 1. So the final total number of valence electron comes 22. Now again 22 will be divided by 8. It goes by 2 times, that is 16, and the remainder is 6. We will divide 6 by 2 and the quotient comes 3. Now to calculate the total number of valence electron, we will add both the quotient, that is 2 and 3. So the total number of hybridized orbital is 2 plus 3 is equal to 5. Therefore the hybridization is sp3d. Now to calculate the lone pair, in I3 minus, one iodine will act as central atom while 2 other iodine will act as surrounding atom. So the number of surrounding atom in I3 minus is 2. Therefore the lone pair is 5 minus 2 is equal to 3. That's it. And to some additional information about this division method, we don't have always to divide by 2. We will divide by least possible number so that the final remainder comes 0, and we will add all the quotient to calculate the total number of hybridized orbitals. So that's it. Thank you.